Today we are going to start a very important concept of solid state physics, and this is actually the concept of reciprocal lattice. Actually, this concept of reciprocal lattice is a crucial concept, or you can say a fundamental concept of solid state physics, particularly in the study of crystal structures and diffraction of waves like X-rays or electron wave, neutron waves. It is a very important tool to deal with such physical phenomena. In fact, this concept of reciprocal lattice is a mathematical construct used to describe the periodicity of a crystal in reciprocal space. When you say reciprocal space, this is actually the dual space of the direct lattice space, or you can say that reciprocal space is actually the Fourier transform of real space. So when you talk about the reciprocal space, in nutshell you can say that this reciprocal space is what? This is the Fourier transform ft of real space. Okay, and so this space is also called Fourier space, or the k space, where k is the wave vector. Okay, but a question definitely will arise in your mind, that why we need the study of this reciprocal lattice if the phenomena uh, already have been discussed in the real space or direct lattice space. What is the reason behind the use of this reciprocal lattice space reciprocal lattice concept? In fact, you have studied the diffraction of X-rays. Particularly, you have studied two treatments of X-ray diffraction, that is Bragg's treatment and the Lowes treatment. And you have seen that actually the diffraction of X-rays occurs from various sets of parallel planes having different orientations, or you can say different slopes, and the interplanar spacing. Okay, actually in certain situations involving the presence of number of sets of parallel planes with different orientations, it becomes very difficult to visualize all such planes because of their two-dimensional nature. So if your aim is to visualize the planes, what will be the technique? Actually, this technique was developed, or you can say this problem was simplified by a well-known crystallographer and named P P Ewald, by developing a new type of lattice which is called reciprocal lattice. Okay, so the idea of the reciprocal lattice was developed by P P Ewald. Okay, so why reciprocal lattice? As I have mentioned here, it provides a simple geometrical basis for understanding the geometry of X-ray and electron diffraction patterns. Okay, and a very elegant tool. It is a very elegant tool to study the behavior of electrons in crystals, that is a reciprocal space being essentially identical to the K space or Fourier space. Okay, and as I have told you that the credit for the development of reciprocal lattice and its application to analyze the X-ray diffraction patterns and the behavior of electrons in periodic crystal, this is due to P P Ewald. Okay. So first of all, we will now know why we have known that why we need the study of reciprocal lattice. Actually, the utility, or you can say the application of this reciprocal lattice is so many in the study of solid state physics. You will see later on in my consequent lectures the idea of Brillouin zone. Actually, the idea of Brillouin zone uh, can be dealt in terms of reciprocal lattice. Okay. At the same time, as I have told you earlier, that the diffraction phenomena can be easily understood in terms of reciprocal lattice, that is the diffraction of X-rays, electrons, neutrons, etc. Okay. At the same time, this study of reciprocal lattice is also very important in study the optical properties of the crystal lattice. The phenomena like dispersion of light waves in crystals can be easily explained by the use of the idea of reciprocal lattice. Okay. So I think you have understand why this idea of reciprocal lattice was developed by P P Ewald, and why it is a crucial and very fundamental concept of solid state physics. Okay. Now in this first lecture on reciprocal lattice, first of all we will know what is this reciprocal lattice, how we can define it, what is reciprocal lattice vector, and what are the different important vector algebraic properties of this reciprocal lattice. Okay. So let us start to know about the reciprocal lattice vector. Okay. As I have told you that this idea of reciprocal lattice was introduced by P P Ewald due to the particular problem of visualizing the crystal planes from which the X-ray diffraction takes place. Actually, this problem can be simplified in a particular manner. Actually, the direction of each normal represents, actually when you want to know the idea of reciprocal lattice, you can see this figure. Actually in this figure I have shown two families of parallel planes. You can see it here. Actually these lines, parallel lines, which I have marked by let us say planes 2. Actually these are the edges of the planes. Actual planes have not been shown, only the edges of the planes have been shown. So in this figure these parallel lines represents planes. These are not lines but they represent planes, and I have marked that these are the planes 2. Okay. On the similar manner you can see that this these parallel family of parallel lines which have been drawn vertically, these are also the parallel planes. Okay. So in this figure I have shown two families of or two sets of parallel planes. Okay. I have marked it here that these are the planes 1. Okay. Now to develop the idea of reciprocal lattice, we choose an arbitrary origin. You can see this figure. O is an arbitrary origin. Okay. And we draw normals from this arbitrary origin to the families of parallel planes. Okay. So you can see this line which I have drawn here, let us say this is OP. This OP is actually the normal drawn from the arbitrary origin O, and this is the normal to all the planes 1. Okay. And in the similar manner from the same origin O, again a normal is drawn on the set of parallel planes marked by 2. Okay. So you can see these normals uniquely define the orientation or represent the orientation of the parallel planes. Actually the orientation of the planes marked by 1 can be represented by the direction of this normal OP, and similarly the orientation of the planes marked by 2 can be represented by this normal marked by OQ. Okay. Okay. Now, the length of the parallel is taken just inversely proportional to the interplanar spacing. Okay. If you can say that the interplanar spacing in case of the set of parallel planes marked by 1 is, let us say, d. D is the interplanar separation. Okay. In fact, in that condition, you can say or you can say d1, not d. Okay. And the interplanar separation in case of the parallel planes marked by 2, this is, let us say, d2. Okay. d2. Now, to get the reciprocal lattice point, we take the length of these normals just inversely proportional to the interplanar separation. Okay. So, the length of this normal OP is taken, let us say, sigma 1, and this sigma 1 will be inversely proportional to d1. And so you can say that sigma 1 is equal to k over d1. Okay. And in a similar manner, the length of the normal which is perpendicular to the set of parallel planes marked by 2, whose interplanar separation is d2, the length sigma 2 is taken inversely proportional to d2. So sigma 2 is k over d2. Okay. In fact, in most of the cases, the value of this proportionality constant k is taken 1. This is taken 1. But in X-ray or electron diffraction, it is more convenient to take the value of k equal to lambda, which actually represents the wavelength of the X-ray or electron. So, in most of the cases in crystallography, we take this proportionality constant 1. So, we simply say that this sigma is equal to 1 over d. Okay, 1 over d. Actually, all those points, let us say here there is a point, let us say P1 and this is P2. Okay. Actually, these points are called reciprocal lattice points. I have shown in this figure only two sets of parallel planes, but if you can imagine that there are a large number of sets of parallel planes, then we will draw a normal to all the sets of parallel planes from the same common origin, and we will take the length of the normals just inversely proportional to the interplanar separation. Then all the terminating points of the normal are called reciprocal lattice points. So in general, there will be so many points in this reciprocal space, and all these points are called reciprocal lattice points. Okay, I think we have understand how we can actually obtain this reciprocal lattice point. So just as a rule, you can say for getting the reciprocal lattice point, we take an arbitrary origin and draw normals to every set of parallel planes of the direct lattice. And we take the length of each normal equal to reciprocal of the interplanar spacing for the corresponding set of planes. The terminal points of these normals form the reciprocal lattice. Actually, all these facts I have mentioned here for your convenience. I have written these things, and so you can note down these facts in your notebook. Okay. Now, in this way, we can define the reciprocal lattice vector. So you can define the reciprocal lattice vector, which is denoted by the symbol vector sigma. And if you write sigma HKL, it means this is the reciprocal lattice vector, and this will be perpendicular to the plane HKL marked by the Miller indices HKL. Actually, this reciprocal lattice vector is defined as a vector having magnitude equal to the reciprocal of the interplanar spacing, which is DHKL, and its direction is its direction coincides with the normal to the HKL planes. So if we consider that there is a unit vector n hat in the direction of the normal drawn on the set of parallel planes. Let us say these are the set parallel planes, and we have drawn a normal, let us say, in this direction, and then this n hat is the unit vector along this normal. Then the reciprocal lattice vector sigma HKL is directed along this n hat, and as its magnitude is just the reciprocal of the interplanar separation, if this is DHKL, then magnitude of this sigma HKL will be 1 over DHKL, as you have seen, and direction will be along the normal, that is along n hat. So the vector sigma HKL is written as 1 over DHKL times n hat. Okay, where n hat, you know, is a unit vector normal to the HKL planes. Okay, actually, as I have told you earlier, that this constant here may be taken equal to lambda, but we will take this in case of diffraction. In crystallography, in general, the crystallography takes this proportionality constant k equal to 1. Okay, so this is the basic definition of the reciprocal lattice vector. Okay, now as you know, this reciprocal, as you know that actually the direct lattice has a unit cell. In the similar manner, the reciprocal lattice has also a unit cell. So how we can define the unit cell of a reciprocal lattice, and what will be the primitive translation vectors of the reciprocal lattice? Now we will learn about it. Okay, and for this you can see this figure. Actually, in case of direct lattice, you know that the primitive translation vectors are ABC. This A represents the first primitive translation vector. This B represents the second primitive translation vector, and this C represents the third primitive translation vector in case of direct lattice. Okay, and actually these primitive translation vectors, you know, are directed along the 3 crystallographic axes. Okay, actually in this figure I have shown the unit cell of a direct lattice, but here our aim is to define the unit cell of a reciprocal lattice and the primitive translation vector of the reciprocal lattice. Actually, in fact, like the direct lattice, the reciprocal lattice also has a unit cell which is of the form of parallelopiped, as you can see. This is actually the unit cell of a direct lattice which is in the form of parallelopiped, and the unit cell of reciprocal lattice is also in the form of parallelopiped like the direct lattice. But you can see how we can define the primitive translation vectors. Actually, for getting the primitive translation vectors, you have to think about the normals drawn on the set of parallel planes which will have actually the shortest length. In this figure, you can see the plane ABCD. You can see here the plane ABCD and the plane EFGH. See here, EFGH. These are the parallel planes. Okay, and what will be the Miller indices for this? You can see that as the plane ABCD and EFGH. In this case, this plane is parallel to the primitive translation vectors B and C. So for these, the Miller index will be 0. But A does not intersect it. For this will be 1. So these planes A, B, C, D and E, F, G, H are marked by 1, 0, 0 plane. Similarly, the planes A, D, G, H, you can see A, D, G, H. This is the plane A, D, G, H. Okay, and you can see this plane is parallel to the plane BCFE, and this is actually the plane marked by Miller indices 0, 1, 0. And similarly, the plane ABEH and DCFG, this is the plane 0, 0, 1. Okay. Now for getting the primitive translation vector for the reciprocal lattice, we will take the normals of shortest length. Okay, and for this you have to draw a normal on the planes, parallel planes, and the length of these normals are taken as sigma 1, 0, 0, sigma 1, 0, 0. This is the length of the normal perpendicular to the parallel planes marked by 1, 0, 0, and sigma 0, 1, 0 and sigma 0, 0, 1. Okay, actually these are the fundamental primitive translation vectors for the reciprocal lattice. Okay, and how we will define it, now you can easily understand how we will define this primitive translation vector for the reciprocal lattice. And for this you can see this figure. Actually, if the interplanar separation of the plane marked by 1, 0, 0, if it is D1, 0, 0, then in terms of this D1, 0, 0, we can define the volume of this unit cell of the direct lattice. As you know, volume of this unit cell will be what? That will be area of the base multiplied by its height. Okay, so you can see that volume of the unit cell of the direct lattice V, this is actually the volume of the direct lattice unit cell, and that will be area times height, and this height is D1, 0, 0. Okay, and if you will take the area of, let us say, ABE AHA, then you have to take the height as, in fact, D 0, 0, 1. Okay, you can take. And as our aim is to find the reciprocal lattice vector, whose magnitude is actually reciprocal of the interplanar separation, so from here you can easily find what will be 1 over D1, 0, 0. This will be area divided by volume. But you know, from the geometrical meaning of vector product of two vectors, since this plane is designated by the vectors B and C, so the modulus of B cross C represents its area. Okay, and volume is V. And in vector form, you can write this equation as 1 over D 1, 0, 0 n hat, and that will be equal to B cross C over V. Actually, the direction of this vector B cross C is along the normal perpendicular to the plane containing B and C, according to the definition of vector product of two vectors. So this B cross C is along the normal unit vector, that is n hat. So in vector form, you can write 1 over D 1, 0, 0 n hat. This is B cross C over V. Okay. But as you know, here this 1 over d n hat, this represents the reciprocal lattice vector sigma. And so we can write that sigma 1 0 0, this is 1 over d 1 0 0 n hat. And therefore from these two equations, that is equation number 2 and equation number 3, you can easily say that what will be this sigma 1 0 0. This sigma 1 0 0, I have written for this sigma 1 0 0, this will be B cross C over V. But you know that volume of this unit cell is equal to what? V is equal to A dot B cross C. Or you can also write it B dot C cross A or C dot A cross B. All these are equal, and that represents the volume of the direct unit cell. Okay. So sigma 1 0 0, this is defined by B cross C divided by A dot B cross C. And for convenience, this primitive translation vector for the reciprocal lattice is denoted by A star. Okay. So sigma 1 0 0, this is written as A star. You can write the sign of equivalence. A star is equivalent to sigma 1 0 0, and that is defined like this: B cross C over A dot B cross C. Actually, in the similar manner, you can define the second primitive translation vector for reciprocal lattice. This is B star, which is equivalent to sigma 0 1 0, and that will be equal to C cross A over A dot B cross C. Actually here there will be actually B in this case there will be actually B dot C cross A, but as B dot C cross A is equal to A dot B cross C, so in denominator I have not written the expression B dot C cross A, okay, because this is equal to A dot B cross C. And the third primitive translation vector for reciprocal lattice is denoted by C star, and that is actually equivalent to sigma 0 0 1, and that will be equal to A cross B over A dot B cross C. So this is the defining equation for the primitive translation vector of reciprocal lattice, and you should remember this definition. Okay. Actually, in some of the textbook, or particularly the crystallographer, also use another prescription for defining this. Actually, you will see in case of crystallography, the definition which I have mentioned here is more convenient, and this A star is defined by 2 pi times B cross C over A dot B cross C, and B star is equal to 2 pi times C cross A divided by A dot B cross C, and C star is equal to 2 pi times A cross B divided by A dot B cross C. This is just a convention, and in crystallography this definition is more convenient. Okay, so in so many textbook you will also get this definition. Okay. Now after getting the basic concept of reciprocal lattice vector and how it is defined, how the primitive translation vector of the unit cell of a reciprocal lattice is defined, now on the basis of this definition you can learn about some of the important vector algebraic properties of reciprocal lattice vector. Okay. Now see the definition of this primitive translation vectors A star, B star and C star, as these have been defined in equation 4 or in equation 3. You know from the definition of vector product of two vectors that if A cross B is equal to C, then this C vector is perpendicular to both A and B. In other words, you can say that vector C is perpendicular to the plane containing these vectors A and B in accordance with the right-hand screw rule. So on the basis of this definition of vector product of two vectors, you can easily say that this A star will be definitely perpendicular to vector B and C. Similarly, this B star will be perpendicular to C and C star will be perpendicular to A and B. It is evident from this definition. So you can say that A star is normal to B and C. And you know the condition of orthogonality of vectors. If two vectors are orthogonal to one another, that is the angle between two vectors is 90 degree, then their dot product or the scalar product is 0, because A dot B is AB cos theta, and when theta is 90, then cos 90 will be 0. And so since A star is perpendicular to or normal to B and C, so you can see easily that A star dot B, this will be equal to 0. A star dot C, this is also equal to 0. And again you can see that B star is normal to C and A. So their dot products will be also 0. So B star dot C is 0, B star dot A is 0. And you have also seen that C star is also normal to A and B. So C star dot A is 0 and C star dot B is 0. And this is a very important algebraic property of this primitive translation vector of reciprocal lattice, and this will be invariably used in the discussion after some time. Okay. Now let us take the scalar product of A star with A, and you know the scalar product of two vectors is commutative, so you can also say that A star dot A is simply equal to A dot A star. Okay. And A star, from definition you can see that this A star is equal to B cross C over A dot B cross C. So instead of this A star, I have written here B cross C over A dot B cross C. And so you can see this the scalar in the numerator and in the denominator are same, so these two will cancel out and your result will be 1. Actually, in the similar manner, you can see that the scalar product of B star with B and C star with C will be also equal to 1. Okay. Actually, in the derivation of these results, I have used the definition of the primitive translation vector defined in this equation 3. But you also know that these primitive translation vectors may be defined as I have defined it in equation 4. So when we will use the definition containing this factor 2 pi, then what will be our this result? This result will be then A star dot A equal to B star dot B, and that will be equal to C star dot C, and that will be equal to 2 pi, not to 1. Sorry. So instead of 1, using that definition, your result will be 2 pi. Okay. This does not make any difference because 2 pi is a constant factor, but this will be useful in so many physical situations when we will actually use this idea. Okay. Actually, when when you see this result, it appears from these equations that this A star, B star and C star are parallel to A, B and C. It appears. However, this is not always true. In non-cubic crystal systems, such as you can say monoclinic crystal, this is not a cubic crystal. In this case, you will see that A star and A do not point in the same direction. but they are directed in different directions. Okay. So when you say that A star dot A is equal to 1, that means what? That actually means that A star dot A is equal to A star times A cos theta, where theta is the angle between A star and A. Okay, and this equals to 1. It means definitely this A star is the reciprocal of the projection of A along A star. So it is interpreted in this manner that uh, the length of the vector A star is the reciprocal of A cos theta, where theta is the angle between A star and A. Okay, so don't think that A star, B star, C star are parallel to A, B and C respectively in always. It is although true in case of cubic crystal, but in non-cubic crystal this fact is not true. Okay. Now let us see. As you know, if there is a point in direct lattice space, that point is located by a translation vector defined by T, and you know this translation vector actually is used to locate any point in the direct lattice space, and this translation vector is defined like this: T equal to MA plus NB plus PC, where M, N and P are integers. Okay. So if you know the this translation vector T, you can locate any other point in space. Okay, any other point. In the similar manner, when you actually talk about the reciprocal lattice space, then we have to define a translation vector just equivalent to this T. And in this case, actually, in case of reciprocal lattice, uh, which is actually the which is defined in reciprocal space or K space or Fourier space. Actually, in this case, we define a vector which is called reciprocal lattice vector, and this reciprocal lattice vector is defined just on the line of this translation vector T. And if we denote this reciprocal lattice vector by the symbol G, this is defined as HA star plus KB star plus LC star, where actually H, K and L, these are also integers. Okay, these are also integers. Now you can see that this G and T are closely related to one another, where T is a translation vector in the direct lattice space, while this G is the reciprocal lattice vector defined in the reciprocal lattice space. Okay. Actually, if you consider there is a point P having the coordinates HKL, then this point with respect to any arbitrary origin, the position vector of this point is defined by G, and that will be equal to actually this HA star plus KB star plus LC star. But how this G and T are related to one another? And for this, we find the scalar product of G and T. You can see G dot T will be what? As you know, G you have written this is HA star plus KB star plus LC star, and T is equal to MA plus NB plus PC. Okay. Now take the scalar product. As you know that you have just seen that A star dot A star, okay, is equal to B star dot B, and this is equal to C star dot C, and this is equal to 2 pi. We also write it 1, but here I am writing this is equal to 2 pi because it will be more convenient, okay. And at the same time, when you take the scalar product of different entities like A star dot B, A star dot B, or B star dot A, or C star dot A, all those are 0. So here you can say that when you will take the scalar product of this HA star with MA, then the result will be non-zero. But when you will take HA star dot NB, HA star dot PC, all those will be equal to 0. You have just learned. So after taking the scalar product and utilizing the algebraic properties like this, you will get that this product will be equal to 2 pi times mh plus kn plus lp. Okay. Now since m, h, l and np, all these 6 are integers, and the product of two integers is also an integer, and the sum of 3 integers will be another integer, so that this bracketed term is nothing. This is simply an integer, okay. And so I have written, instead of this mh plus kn plus lp, this capital N, and this capital N is also an integer. So what you are getting, you can see that we find the scalar product of G and T, where T is the translation vector in direct lattice space and G is the reciprocal lattice vector. The scalar product of this is just the even multiple of pi, yes, even multiple of pi, or you can say that integral multiple of 2 pi. Integral multiple, n is integer, so you can say that G dot T is equal to integral multiple of 2 pi. Okay. Now let us find a plane wave. You know, e to the power I k dot r is called a plane wave, and so e to the power I g dot t, what will be this? You can see this is e to the power I 2 pi n. And you know, e to the power I 2 pi n, this will be cos 2 pi n plus I sin 2 pi n. But you know, cos 2 pi n, this is equal to 1, and sin 2 pi n is equal to 0. So our result is equal to 1. So this is a very interesting result, that e to the power I g dot t is always equal to 1. Okay, e to the power I g dot t is always equal to 1. This is a very important result, and you will see later on the importance of this result actually in the forthcoming lectures. Okay. And as I have told you that this equation actually indicates that if there is a point having coordinates HKL in reciprocal space, then this G represents the normal to the planes marked by the Miller indices HKL. Okay. So this G is, if you say that this is a plane marked by Miller indices HKL, then this G represents a normal to this plane. Okay. So this is the basic idea of the reciprocal lattice vector, and we will now deal with the very important problems related to this reciprocal lattice vector in the forthcoming lecture. And as you have seen that in after this discussion, it is obvious that every crystal structure is associated with two important lattices, the direct lattice and the reciprocal lattice. The two lattices are related to each other, and what is the relation between them you have just learned. A star is related to ABC, B star is related to ABC, and C star is related to ABC. So you have just learned. Actually, the fundamental translation vector of crystal lattice and the reciprocal lattice have dimensions of what? These have dimensions of length and length inverse, because you have seen that this sigma is just inverse of DHKL. Okay, and so the direct lattice vector has the dimension of length, while the reciprocal lattice vector has the dimension of length inverse. And this is why the latter is called reciprocal lattice. Okay. So you will also see later on in my second lecture that the volume of the unit cell of a reciprocal lattice is also inversely proportional to the volume of the unit cell of direct lattice. Okay. And all these things, what will be the reciprocal lattice to a BCC lattice, what will be the reciprocal lattice to a FCC lattice, all these things we will learn in the forthcoming lecture. So I hope you have clearly understand this basic idea of reciprocal lattice, its importance in this lecture. So thank you very much.